Hello everyone. In this lecture, we are going to discuss logic gates. Now, what are logic gates? These are fundamental building blocks of any digital circuit, and these are electronic devices that perform logical operations on one or more binary inputs to produce a single binary output. They do logical operations and they form a fundamental building block of all digital electronic circuits. Now, these operations that the logic gates do perform are based on Boolean algebra that deals with variables that have two possible values. That is, it can be a true value or it can be a false value. It can be 1 or it can be 0. It can be high, it can be low, depending on the configuration. In some instances, actually majority, you find that high is represented by 5 volts and low is represented by 0 volts. Now, we have said that logic gates are very essential in digital electronics and computer science for a number of reasons. One, they are very fundamental in digital computation. They are the foundation of all digital computers you see around. They form a basis of all digital operations performed by computers, and that is the operations are ranging from simple arithmetic to complex algorithms that involve both logic and arithmetic operations. Now, we also find them in data processing. Logic gates can be used to process and manipulate digital data in various electronic devices, and these are the smartphones, tablets, digital cameras, etc. They are also used in control systems. Logic gates are crucial components in control systems because they are used to control operation of devices based on specific conditions or inputs. So based on either high or low, you are able to respectively switch on or switch off an electronic circuit and thereby being in charge of your system. Then they are also very important in memory storage. Logic gates are used in memory circuits to store and retrieve digital information in electronic devices. And therefore, that's why you find the random access memory and the read-only memory are one or some of the examples of the electronic devices where logic gates are used as a base for memory storage. Then we'll also find that these logic gates are very important in digital signal processing. Such applications, will find them in telecommunications and the processing, of course, to manipulate and analyze digital signals. Now, in a nutshell, logic gates are forming a fundamental component of digital electronics, and they do enable the design and implementation of a wide range of digital systems and devices that form the backbone of the modern technology. Now, we have a number of types of logic gates, each performing a specific logic function or operation. We have the AND gate, and this outputs a true or a high value only when all of its inputs are true or when all its inputs are high. We have an OR gate and a NOT gate. For an OR gate, it outputs true if at least one of its inputs is true or is high. And then a NOT gate, also called an inverter, outputs the opposite value of its input. Now, an example of where these three basic logic gates are employed, we find the AND gate in switches. For example, in series switches, when you put switches in series, you find if one of them is open, then you never have lights on. If you have all of them open, you'll never have lights on. If you have all of them closed, then you'll have lights on. For a NOR sorry about that. For a NAND gate also, you can compare it with the mathematical operation of multiplication. So if I get x multiplied by y, it is analogous to a NAND gate operation. Of course, I'm saying 0 times 1 is equal to 0, 0 times 0 is equal to 0, 1 times 0 is equal to 0, but 1 times 1 is equal to 1. That's all I'm trying to mean. Then a NOR gate is analogous to having switches in parallel. When one switch is off, you can still have lights on. When all switches are on, you have lights on. But when you have all switches off, automatically you cannot have lights on. And we are saying it is also analogous to mathematical addition. When I get one input plus the other input, if at least one of them is high, I always have a high as an output. But if I have all of them being 0, then I'll have an opposite output, I'll have the same output, which is going to be 0 or low. So a NOT gate is an inverter because if I have an input as 1, it will always give me 0 as an output. If my input is low, my output is always going to be high. Now we still continue with logic gates, and a NAND gate is an AND gate negated. A NOR gate is an OR gate negated. Now, what is an XOR gate, or what we call the exclusive OR gate? This exclusive OR gate outputs true, that is high or that is 1, if exactly one of its inputs is true. As long as you have only one of its inputs being true, then you are going to have a true as an output. What about the XNOR gate? This is an XOR gate negated. In other words, we are saying it is a type of logic gate that outputs true if both of its inputs are the same. So if you have low at the input, the output is going to be high. If you have high at the input, the output is going to be high. That's what we are meaning. But if you have or you have high and low, then the output is low. If you have low and high, then you have the output as low. In other words, it behaves as an OR gate followed by a NOT gate. Now, the truth tables, as I have said, these are going to represent it's actually a table that is going to represent the outputs of different logic gates. Now, already I said, if you have a low and a low at the input, for two inputs to going through a NAND gate, we are saying take it as if you're getting 0 times 0. You always get an output as 0. But this is analogous. But in rare cases, in rare scenarios, multiplication and a NAND gate are not the same. So in reading this, if I say Z is equal to X and Y, there is a dot. That dot means AND. So 0 and 0, you'll get 0. 1 and 0, you'll get 0. 0 and 1, you'll get 0. 1 and 1, you'll get 1. And therefore, we have implemented a NAND gate. Now, the OR gate is going to give you a high as long as you have one of the inputs being true. And if all of the inputs are low, then you're going to have a low output. And we said this is analogous to an addition mathematical operation. Then a NOT gate, of course, this is an inverter. You have one or high input and you have a low output. You have a low input, you have a high output. Then an AND gate, we said it is an AND gate negated. So here, 1 and 0, you'd get 0. But because it is negated, you have 1. Then this is how we can simplify it, how we can indicate it. We can have x and y complemented. So the complement of x and y gives you a NAND. So if it is a gate that is having that operation, then we are going to call it a NAND gate. So 0 and 1 would give you a 0, but because it is negated, it gives you 1. 0 and 0 would give you 0, but because it is negated, you get 1. 1 and 1 would give you 1, but because it is negated, you get 0. Then an OR gate, we said it is OR gate negated. So 1 and 0 would give you 1, but because it is negated, you get 0. 0 and 1, you get 0. 0 and 0, you would get 0, but because it is negated, you have 1. A 1 and 1, you do get 1, but because it is negated, you get 0. So this is read as X or Y complement, and that would give you a NOR gate operation. Then XOR, we said it will always give true as long as we have at least one of the inputs being true. At least one gives you a true. At least one gives you a true. And the rest would give you 0. Then the XNOR gate would therefore give you the exclusive NOR gate. And the exclusive NOR gate, we are saying it is going to be XOR gate or exclusive OR gate negated. So where we had that at least one of the inputs being true, that the output would be true. In this case, the output is going to be false. So at least one, the output is false. At least you have a 1 or a high as input, you have the output as low. So where they are the same, similar inputs, high and high, you get a 1. High, we said low and low, you get 1, and high, you get 1. Ladies and gentlemen, thank you for listening. Thank you for following us. Thank you for supporting us. Please subscribe, like, and share.